everybody. It's a pleasure and an honor to be here with you today to talk about hydrogen-assisted combustion and how it can save fuel and reduce emissions. But first, I'd like to start with a question and a story. So how many people here have been to Beijing and Mexico City? Just a few? Well, I had the opportunity for the first time to go to Beijing in late January of 2013. And I emerged from the airport at 12:30 a.m. I walked out to the street, I looked up, and I saw this glow of the sodium vapor lamps against this gray-white fog in the sky. I inhaled, and I said, am I in Atlanta at JR's barbecue house? It was disgusting. And then the next day, they took us to the Great Wall embarkation point, an hour outside of Beijing. And the fog was still there in the middle of winter. You probably saw this in the news. That's when Beijing's weather was in the news, or air quality was in the news. Now, I haven't been to Mexico City, but we are doing business there, and I'm told that there's a fairly high probability that if you put a canary on your balcony at night, it will be dead by morning. So reducing the impact of diesel fuel, it's not the only bad actor, but it is an important bad actor, and reducing its impact is important for climate change and clean air. The logistics industry has been attempting to do this through regulation, through the adoption of emissions abatement equipment. And what they found over the last dozen years or so is that it's hurting their bottom line. So all these companies you see here, Schneider, FedEx, UPS, they're all reporting the same things. An increase in maintenance costs, an increase in cost per mile or CPM, an increase in training hours for their people to learn how to manage this new abatement equipment. In 2004 and in 2007, the industry released new fuel-efficient tractors. FedEx reported that their tractors were 33% less reliable. And then in 2010, it only slightly recovered through all that time. Less reliable tractors, all for only modest fuel gains, and all this for more expensive tractors. UPS corroborates this. Far more breakdowns they saw with these new tractors, far higher maintenance costs, no more million-mile tractors. So we all want sulfur out of the diesel, but you know sulfur is a really good lubricant. You take it out of the diesel fuel, you have more maintenance issues. And they reported, UPS, a more than doubling of the cost of their tractors between 2000 and 2011. So what we found is market pain increasing for these fleet owners over the years. And in 2008, fuel became the #1 ops cost. You can see here that their fuel is almost 38% of their operations cost. Their cost per mile nearly tripled between 2003 and 11. So what are their choices to reduce emissions? Either they have to buy a new tractor, they have to put this equipment on their older tractors, or they can do nothing and get hit with fines. Now, the new equipment we're talking about is usually in two forms. It's diesel particulate filters, or DPFs, or selective catalyst reduction units, or SCRs. And each of those come with their own attendant maintenance costs. For DPFs, you have to do a periodic burnout. You can see on the bottom picture. And then for the SCRs, it comes with a consumable, a liquid called diesel exhaust fluid, sometimes called AdBlue. This is a urea catalyst. Now, at the bottom, you see that there were two firms that failed to comply. The first one was a Bakersfield, California shipping company in 2013 that got hit with a $230,000 fine. The second one was $500,000 from a waste hauler in California in 2009. So what we have is a situation where fuel is going up for these people, the maintenance is going down, and if the tractors are unreliable, they're sitting in the shop, they're not producing revenue, and the fleet owner has to rent another tractor. And now they have more equipment to maintain. They're in deep pain, and they need relief. We provide that relief. We have a system that installs in 2 hours on a vehicle. It connects to the vehicle's battery and alternator system, and then we run 2 hoses up to the air intake. And these 2 hoses contain pure hydrogen and oxygen. We make this hydrogen in real time, on demand, through PEM electrolysis, which I'll explain in a minute. The PEM generator creates pure hydrogen, and that goes up to the low pressure side of the turbo before going into the engine. So we introduce it on the air side, not the fuel side. And then below, you can see we have a tank, and that holds distilled water, and that distilled water lasts for somewhere between 1,000 and 1,500 miles. And so the refill is less frequent than even the diesel refueling. So what is PEM electrolysis? Well, PEM stands for proton exchange membrane, or sometimes polymer electrolyte membrane. They're interchangeable, and it's really a fuel cell run in reverse. So you may know that a fuel cell combines two reactant gases, hydrogen and oxygen, maybe methane and oxygen, and the reactant product is water and electricity. Here we're taking electricity and we're splitting the water into their constituent hydrogen and oxygen. Now the difference between this and your garden variety high school electrolysis experiment is that we don't need to add an acid or a base to the water to make it conductive. It's just pure distilled water. So let's take a look at how it works. You're looking at the inner box that contains HydroPhi's HydroPlant hydrogen on-demand system. This box sits inside a sturdy steel box that can be mounted external to a vehicle. This is the sanitary fill port where pure distilled water is added. It is extremely important only pure distilled water is added, as this will affect the life of the PEM stack. On the side here you can see two separate gas hoses, hydrogen and oxygen. These are normally sleeved in stainless steel braided cables for running up to the engine compartment for injection into the air intake. You can also see the hoses for the heat exchanger, used to maintain a consistent water temperature. HydroPhi's HydroPlant system is extremely easy to use. The in-cabin dash-mounted display enables the user to remotely start the system. After running through a 30-second system self-check, power is supplied to the PEM electrolyzer, and hydrogen production begins. From room temperature, full rated flow can typically be achieved in as soon as 5 minutes. The display will show the driver when water is low or out, and will also notify if there are temperature, pressure, or current exceedances. What we're going to do now is show you the power of pure hydrogen and oxygen. This sandwich bag is being filled with the equivalent of one single drop of water. When split from a liquid to a gas, water undergoes a volume increase of about 2,000 times. When this gas is inducted into the air intake of the engine on the low pressure side of the turbocharger, it enriches the fuel and allows it to burn more completely and more cleanly, providing better fuel economy and reduced emissions. Now pardon us as we cover our ears. So I'll be glad to do that in the next room upon request. Anybody wants to see it again. So what you just saw was the inner box that contains the PEM unit. That inner box is placed within this outer box, this sturdy box, and that gets bolted to the back of the truck or inside the bus. So I just want to summarize now the differences between this approach and this chemical electrolyzer approach, which is more ubiquitously found. First of all, we're creating pure hydrogen and oxygen. They're creating this mixed gas called hydroxy, and that's inherently more dangerous. We don't use a caustic electrolyte like potassium hydroxide. They do. We just use distilled water, pure distilled water. And our conductive plates are made out of titanium. Typically, they use 316L stainless steel. That's surgical grade stainless steel. Now, that's very corrosion resistant, but trust me, if you stick those plates in 130 Fahrenheit pH 13 water, it will leach iron and chromium over time. And if you remember the movie Aaron Brockovich, hexavalent chromium in water is a big EPA no-no. So what are the advantages of our system? We've seen fuel savings anywhere between 12 to very nearly 25%, and that's based on the size of the vehicle, the age of the vehicle, and the driving profile. We've seen some dramatic reductions in greenhouse gases. The drivers report an increase in horsepower and torque, and reduction in maintenance costs. So the oil stays cleaner longer. There's about a 50% reduction in the consumption of AdBlue, and then fewer DPF burnouts over the life cycle of the tractor. We designed this to be a flexible and extensible architecture so that we could grow the system into different applications over time. But the most important difference is that we took a determined approach to differentiate ourselves from those in the market by making this really ruggedized sufficiently to rattle around on the back of the truck, which we did not find anywhere else in the market. The PEM is built to DoD specifications. We used design simulation to ensure that components were robust, rugged, and reliable. The electronics are all automotive grade, so they're good to 125 centigrade. We did extensive lab testing. We ran the system in an oven at 127 Fahrenheit to know that this thing could be strapped to the back of a truck in the middle of a rack in the middle of the summer and not skip a beat. And finally, we did vibration testing on a shake table to ensure that all the components would survive. So we feel like we have the most rugged system on the road today, and these systems have been running in Mexico City for very nearly 11 months now with no failures. The results, the fuel results from Mexico are actually very impressive. You see here just over 18% and very nearly 16% for a couple of city buses. The drivers actually buy the fuel themselves, and they know to the peso what they spend every day on fuel. And because these routes are the same every day and very well known, we have a very high confidence in these results, and we've measured very low dispersion in the data that's been delivered to us. Similarly, we've done emissions testing. First, we did some testing on our own in-house 5-gas analyzer on a genset, and you can see between the left and the rightmost of the strip charts there, that's the delta in greenhouse gas emissions that's represented in that box below between the genset being turned on at no load and then 20 minutes in at 50% load, where the thing is now hot and off-gassing like crazy from the engine and the exhaust manifold, and then, of course, pulling more fuel because it's under load. And so that's a very impressive result. What it turns out for Mexico City, what they care about is PM, or particulate matter, and specifically PM10, which is a measurement of the mass of 10 micron or larger particles in an exhaust stream per unit time and distance. And as you can see, I hope you can see that we've got a very nearly 60% reduction in the PM10 count. And that's important because it's now taking these buses from exceeding the PM limit that's in place since this September, last month, and now bringing it under that limit. This now enables the possibility for these bus drivers to not have to buy new equipment, but to keep their old equipment. And that is about to be blessed by the Mexico City government. And then below, it's just an indication of how rapidly the system responds to the electrolyzer being on and off. The green line shows a constant 1,975 RPM as measured on the dynamometer. And then you can see the instant the PEM stack is turned off, the PM count starts to rise. Those tick marks are a half-second intervals. So it's a fraction of a second, and you immediately see the impact. A wide variety of commercial applications in small, medium, heavy-duty vehicles, small buses, and small specialty vehicles such as waste haulers. We can also address construction and agriculture equipment. Eventually, the largest would be marine applications where you'd have tugs, barges, workboats, fishing vessels, and then some of the equipment that Caterpillar showed. Eventually, we can do very large quarry and mining equipment. The size of these markets are just staggering. So we're going to focus on older engines, no new engines, but just the older engines. These are the engines that are so-called single pulse injection, the old style injection systems, because that's where we work best. So out of this 400 million engines, there are still tens of millions of these that are the older style injection systems that would fall in our sweet spot. We could never catch them all. It's a very, very large market. If you do the math to look at the value to the fleet owner, the ROI, I've shown here the European and the US case on the left at 3 different fuel efficiency levels, 12, 16, and 20%. And so your ROI is going to be a function of your price of fuel, how many miles you drive per year, your baseline fuel efficiency, and then what % fuel savings you can achieve. And so you can see that for the US case, that ROI is somewhere between 13 and 22 months. And in the European case, where fuel, of course, is more expensive, 7 to 13 months. And that's not accounting for the possibility of accessing any federal or state incentives for this kind of equipment, nor accounting for the possibility of monetizing carbon credits, each of which could further shrink those ROI timeframes. For the CFO, he would care about his return on assets, and we show in this middle case on the right, the 16% case, a 5 times return on asset. I just want to touch on our go-to-market strategy. As I mentioned, we'll start on the small buses and trucks and small trash trucks. We've got a program in Mexico City. They're talking about 100 to 1,000 buses to start and many thousands more. Monterrey and Guadalajara are next. And then we have a subsidiary set up now in Poland, and we're about to start with an install next week on 2 buses in Poland. And as I mentioned, as we grow the system, we would move to larger over-the-road vehicles, and then eventually to these larger systems, the mining and quarry equipment and the very largest systems, the marine systems. This is a progressive geographic rollout that we have planned, where we start in Mexico, Central South America, and Eastern Europe, and then eventually go to Western Europe and North America. And as you can imagine, over time, we would be doing business or try to do business in the places where it's more difficult, which would be China and India and Africa. And then parenthetically, we see value in the $100,000 in helping us scale dramatically to these largest of systems, where we're going from producing 4 to 5 liters per minute of dry hydrogen to needing dozens and dozens and dozens for these very largest systems. We're talking about much bigger electrolyzers, much higher amp draw, and so that's the development that we would foresee with that prize. And then finally, the team, Roger Slotkin, 40 years of starting businesses and turning them around, and experience in offshore manufacturing. Mark Robinson, one of our directors, has been a consultant to over 300 renewable companies. Reed Meyer, our COO, comes from the oil and gas industry, and specifically the fugitive emissions business with gaskets and valve experience. And then myself, recidivist entrepreneur. This is my 11th startup, with several of them being out of Georgia Tech. And so I thank you for your attention, and I'll be happy to answer any questions.
Questions?
So we've heard a lot of talk about the 3% or 1% on the high sulfur fuel for shipping. Can you talk about how your device might cut the sulfur dioxide from high sulfur fuel?
Sure. We were actually asked this question by the folks in Brazil who have high sulfur fuel for their logistics fleets. And it was kind of a cursory look by me, but it looks like the chemistry is such that the hydrogen can help pull out some of the sulfur, because to get to H2SO4, you have to go through several steps, and it's not clear that you can make it all the way with the addition of hydrogen. So there's the possibility that we can reduce that a little bit, but we have not done the experimentation on that.
Obviously, well, here's one. 2.
Can you tell us a little bit about the energy balance? You said you were looking for money to build bigger systems. What is the amp draw of the small system and the larger system, and how does the balance turn out?
Sure. I'm glad you asked that question. The conclusion or the assumption that everybody initially makes is that this does not work energetically. And that's true if you think about using the hydrogen as fuel. You can't break water apart and hope to get more back. But we're using the hydrogen as a fuel additive to help the fuel burn more completely. And so the lower tailpipe emissions is a result of using more of the fuel that goes through. And it's the energy in that extra fuel that gives you the savings and pays for running the unit. Our unit in the other room, which is good for small trucks and buses, is about 1,100 to 1,200 watts running full bore. Now, when you talk about very large engines, marine engines, Faraday's law still applies. As the electrolyzer grows, the amp draw grows, and you're probably looking at systems that are several hundred amps. But as long as the fuel savings is there and it's burning the fuel better, then that's where the energy comes from to run the system.
One more over here.
Very good presentation, thank you. How would this technology be integrated into natural gas engines? How would it compare? A lot of fleet vehicles are considering, going over to natural gas.
Sure, another good question. So we have not specifically targeted natural gas engines. We certainly could, because we would have a beneficial effect. I can't tell you how much, but you may recall that sort of in the first incarnation of the hydrogen economy, there was a term that was flying around called hythane. And hythane was exactly that. It was hydrogen mixed with natural gas to, again, improve the combustion and improve results. So there's every possibility that we could be beneficial. Now, the value proposition to a fleet that decides I'm going to convert my fleet to natural gas, they're paying for that equipment, they're paying for the infrastructure, so they're kind of saying, I'm done. I don't want to add another bolt-on for perhaps an incremental savings of a few percent. So we haven't aggressively targeted that. But in principle, there's no reason why it wouldn't work.
Bill's got a question.
Two quick questions. One, have you done mean time between failure analyses for your base unit? And the second, for the larger units, have you looked at just ganging them together? That seems like a logical thing, and you've concluded not. I'm just curious why.
So to the first question, we've had enough field experience. I would say we wish we had more field experience, but again, we've had units running for months and months and months and months in the field. And so we know where to look. And so far, we've seen no major failures. We're specifying, so for the distilled water, the pure distilled water, we have an onboard filter. And right now, we're specifying that to be swapped out every 6 months. It's resin bead media filter. We've taken filters back that have been out there for 6 months, and they still look good, but proactively, we're going to switch them out after every 6 months. Beyond that, the most costly component, which is the PEM stack, we believe is going to last, based on information given us from the vendor, that it should last 3 years in the field, maybe 4 years in the field at 2,500 hours a year. They've tested out to 40,000 hours, but at much purer water conditions. Those are the two main areas. Otherwise, you just have, a couple of pumps and a couple of fans, and they're kind of automotive rated, so we're not that worried about that. The second question about the scale of the system, it is quite probable that initially, if we wanted to scale up, we could gang 2 or 3 or 4 of these systems together. In fact, we wrote a patent around that we just filed this past summer. But obviously, when you get beyond maybe 3, you got to start thinking about a different strategy, just because from the cost of goods point of view, it makes sense to scale up to larger electrolyzers and beefier electronics.
We've got one over here.
Thank you. In shipping, and I'm sure this is true in a lot of other industries as well, modifications to engines it's not something that you just do lightly, because there are very often concerns around warranty being voided. Would you like to comment a little bit
Sure.
on that?
We are going to have a Lloyd's of London kind of policy for the truck and bus fleets, so that if it could be proven that anything was due to the system, then it's covered. It only adds a couple of $100 to the total price of the system. But if anything, we're seeing that the benefit of the hydrogen in cleaning up the engine and keeping it clean. So hydrogen is a reducing atmosphere, and it actually will strip carbon off of the engine. And with less carbon on the engine, you're going to have less wear. So we have every reason to believe that it can extend the life of these engines.
As a follow-up question, have you had those discussions with the OEMs, the engine OEMs?
No, we have not, because our strategy has been to go as an aftermarket retrofit, mostly to the older trucks and buses that are already out of warranty. And in fact, I can tell you that anybody that's got single pulse injection, they're probably out of warranty.
Great. Very thorough. Thank you, John.
Thank you.
Take care.